And so we are going to move now. So this concludes the introduction, and we're going to start to move on to the actual hands-on tutorial. As I mentioned before, to do this, we're going to use an online version of the GUI. So please, if you haven't done yet, please go to this link, netpyne.org/GUI, and you should see this GUI in your screen. Again, you can also download these slides, which contain step-by-step instructions of what we're going to do. So if you get lost during the tutorial, don't worry, you can go back to the slides and just check where you left off and continue from there. And also you will see that in the GUI, the tutorials are already sort of predefined, so you can load them in a very easy way, just going to the tutorials menu. So if you get lost, you can just load the completed tutorial and play around with it.
All right, there we go. So yeah, welcome to the NetPyNE GUI. I hope you've got big monitors or 2 monitors so you can have the presentation up next to the GUI. It'll make things easier. But yeah, go to your browser, netpyne.org/GUI. You should see this guy. And the first thing to notice is all the tabs at the top are the steps you have to take to build up a network model. You have to start by defining your cells, move on to populations, add synaptic mechanisms, add the connectivity, stimulation sources and targets, your general configuration, how long does it last, and any specialized plot settings you want to have. One thing to notice is that on the lower left, there's a little expand arrow, and all of these are also available in the sidebar, so you can navigate either way. One thing to point out right now, it's already been mentioned, but there is a Jupyter notebook built in to the NetPyNE GUI. So we can click on that little Python button, and we get a Python notebook that is automatically synced with everything going on in the model. So just to show so what variables are currently available are Jupyter Geppetto, NetPyNE Geppetto. And Salvador will talk a bit more about this coming up, how to interact with code and with the GUI. For me, I'm just going to use the GUI. So yeah, so let's go ahead and start by defining a cell type. So in our Cell Types tab, we'll click the plus above cell. And it's quite easy to start from an empty cell and build it up, but we're going to start with the ball and stick HH cell, just so you don't all have to type everything in. All right, so now we've got our cell type here. It's automatically called cell type 0. If we click on that, we can rename it. And let's go ahead and rename that PYR for pyramidal cell. Okay, so we imported it, we named it PYR. If we click on section, we can see the existing sections inside this cell model. And it's a ball and stick model, so it's just got a soma and a dendrite. And the soma, you can go to the geometry, 12 microns long, 12 wide, axial resistance, membrane capacitance, and so on. So yeah, to get here from scratch, we would just have to type in those numbers. That's not a big deal. Looking at the mechs, it's got a Hodgkin-Huxley mechanism with some parameters set. And the dendrite has, it's only 1 wide, but 200 long. And it has topology. So it has to connect to the soma. It's its parent section, connects at the end of the soma, connects at the beginning of the dendrite. Okay, so we've got a cell type now, our pyramidal cells. Now let's make a population to hold those cells. So we'll click on the populations tab, click the plus button to add a population. And we're just going to call this one E for excitatory. One sec, E for excitatory. The cell type, the only one we have available is the one we just imported, PYR. For number of cells, we're going to put in 40. And you can also choose it versus density or grid spacing. You've got different ways to lay out your model. We're just going to leave the defaults in place for now. So we've got we've got cells, and we've got a population. So we can actually look at our network already. So in the upper right, go ahead and click on Create Network. And now we can see we've got our 40 cell models here. And we can move these around in 3D, zoom in and out. One thing that makes this a little nicer, up on the upper right here is the control panel. And if you click on that, you can set colors for your populations or for individual cells. Since we only have one population, we're just going to apply random colors to these cells just so we can kind of tell them apart. Without having run a simulation, most of the analysis plots aren't going to do much. The 2D net plot, however, will show the location of our neurons in the X and Y. We haven't added any connectivity yet, so they're just sort of separate neurons floating in space right now. So yeah, let's go ahead and go back to edit, and we'll add the rest of our model. So if we want to connect neurons, we're going to need a synaptic mechanism to do it. So we're going to click plus above synapse. And instead of synapse 0, we'll just call this EXC for excitatory. We'll just use the default X2 syn, 2 exponential synaptic, pretty standard model. We'll have a pretty fast upward time constant and a slower downward. And that's all we need. So now we have to define how we're going to connect these neurons. So we're going to add a conductivity rule in the Conductivity Rules tab. And let's go ahead and call this, we like to give descriptive names to all our variables. So we're going to call this E to E. So we've got an excitatory population called E, and it's just going to feed into itself, E. On the postsynaptic neuron, we have to decide where it's going to attach. And looking at our segments, we know it has a soma and a dend. So we're going to connect to the dendrite. So all the synapses from a neuron will attach to the dendrite of the postsynaptic cell. And we'll just do that in the middle of the dendrite. It's the standard default neuron setting. Our synaptic mechanism, the only one we have, is the excitatory one. So we'll choose that one. And for connectivity, you can use convergence, which is how many cells come on to one cell. You can use divergence, which is how many cells does one cell connect to. But the simplest one is just to use a probability of connection. So we're going to set a 10% probability of connection. So for each of these cells, there's a 10% probability that it'll connect to any other one. 1 synapse per connection. We're going to give this a weight of 0.005, which is a pretty good, good results for this. We'll give it a 5 millisecond connection delay. So after the action potential, we say it takes 5 milliseconds to travel down the axon, hit the synapse, and affect the next cell. And yeah, you can put plasticity mechanisms in, but that's more complex. We're not going to do that right now. So we've got our conductivity. Let's go ahead and go back to our network real quick and just take a look. So hit that Create Network button. And the 2D net button, we're going to have to run the simulation to get this. So yeah, we're going to click the little launch button to run the simulation. It's going to reset this. But now, if we look at that 2D net plot, we can see that all our cells are in place. And we also have, I just got some sort of message, if somebody could verbally tell me it. Yeah, we can see all the cells, and the plots are all interactive. So if you hover over it, you can get more information out of it, and so on. You can move plots around. So yeah, feel free to play with moving plots around and stuff. For now, we'll go back to edit and finish setting this up. Without a source of stimulation, this model is not going to do anything. So we are going to add a stimulation. Let me just catch up on the stimulation inputs. All right. So stim source 0 is the name it's given, but this is going to be an I clamp, a current clamp. So we'll just call, all right, let me try a refresh. And yeah, it looks like it saved everything. So good. Conductivity rules still there. Stim sources. Okay, to the I clamp. We're going to name it I clamp 1. There's a variety of things you can use as a stimulator: the current clamp, the voltage clamp, net stims, etc. We're just going to use an I clamp for now. We're going to give it a delay of 20 milliseconds. So when the simulation starts, it's going to wait 20 milliseconds, and then this current clamp will kick in. We're going to have it last for 5 milliseconds, and we're going to give it an amplitude of 0.1 nanoamps. So this defines the stimulation source, but where is that going to go? We have to define its target. So let's add a target. And again, we're going to try to give all these things descriptive names. So we're going to call this iClamp1 to cell 0. Our stimulation source, we only have the one we made, iClamp1. The target section is going to be the dendrite. So we have to type in dend. And the target location, we'll have this at the very end of the dendrite at 1. Just one sec here. Maybe give them time to copy param values. Okay, if I'm going too quick, let me know. So yeah, so we've got...
Going too quick.
Is it, what's that? Too quick?
Yep.
Okay, I'll slow it down, sorry. Okay, so yeah, let's go back to our stim source. So that's an iClamp1, or an iClamp, we call it iClamp1. 20 millisecond delay, 5 millisecond duration, 0.1 nanoamps for the amplitude. Okay.
And Joe, maybe you can show again the connectivity rules in case someone missed the parameter values?
Yeah, absolutely. So the conductivity rules, we're calling ours E to E. It's from our E population to our E population. The postsynaptic, oh, and I didn't finish this. Thank you, Salva. So our postsynaptic section is going to be the dend. The location is 0.5. It's that excitatory synaptic mechanism. 0.1 probability of connection, 1 synapse per connection. 0.005 is the weight, and a 5 millisecond connection delay. Okay. So then we have to define this connection. What are the presynaptic cells? What are the postsynaptic cells? So we click on our presynaptic cell conditions here. And we've only got one population, so our presynaptic cells will be population E. You can also define conductivity based on cell type or range of locations. You know, there's lots of options for how to define conductivity. For the postsynaptic cells, they're going to be the E population as well. And yeah, so that should completely define our conductivity rules. E to E. These keep disappearing, but hopefully it won't cause a problem. Excitatory, 0.1. Okay, so we've got, that defines our conductivity. So back to our stim sources. And again, we chose an iClamp, added a plus, chose an iClamp, and named it iClamp1, 20 millisecond delay, 5 millisecond duration, 0.1 nanoamp amplitude. For the target, we got to give it a name. We're just going to feed it into cell 0. It's going to hit the dendrite of that cell at the end of the dendrite, so at location 1. The conditions, we don't want to target a population. We just want to hit one cell. We don't want to target a cell type, just one cell. At the bottom, we can add a GID, a global indice, for the cell we want. So we're going to add cell 0. And so, yeah, so this stimulation target only goes into cell 0. Now we will set our, okay, so that wasn't too much, right? It should be pretty easy. There we go. Okay, so now we got to configure our simulation. So we're going to shorten this up, but we don't need it to be so long for this simple one. And also, we don't need such a small time step for such a simple simulation, so we're going to make it a larger time step. It'll just make it simulate more quickly. So again, we're going to simulate for a duration of 200 milliseconds, time step of 0.1. Okay, and we're just going to leave everything else here at the defaults. Now we have to go to record to say where we're going to be recording from. So we're going to record from that cell 0 because we've got stuff happening there. And we have to say what we're going to record. We want to record some traces. We want to know what the voltage is what the voltage in the soma is like, and what the voltage in the dendrite is like. And this requires a little bit of pseudo code. You have to name your variable. So for the voltage in the soma, we'll just call it V soma. And then in the NetPyNE itself, you enter this as a dictionary. So with these curly brackets. Okay, and the voltage in the soma, you need to know which section that's coming from, and that's the soma. you need to know the location it's coming from, and we'll just do the middle of the soma, 0.5. And you need to know the variable that is being recorded, and the voltage is called lowercase v. So this is how to add a way to record the soma from these cells. Okay. So once you've got that in, you can click plus. One trick is if you hit here and enter, it'll tell you an incorrect format and give you an example, and then you can actually cut and paste this into here. Anyways, let's copy this, and we'll add it to our traces to record from. But now we made that a capital V, so for consistency, we'll do it again. VDEND. The section is now DEND. And let's record from the end of the dendrite where the input's going in instead of the middle. So we'll go location 1.0 and the variable V for the voltage. Okay, so now we're going to record 2 traces from cell 0. And yeah, that's all we're going to need to do for that. One final thing is you don't have to do anything in the plot settings for the plots to run once you've run the simulation. But if you want to adjust those plots, then you need to go to plot settings and adjust them. And we're going to adjust the traces plot because first of all, we're only going to do the one cell we're recording from, so cell 0. Okay, so you click in the cells to include box. Go down to GIDs and make sure you get a check next to cell 0. Starting time and anytime we leave there. And the reason we want to change this is because we want to overlay the data. We want the dendrite voltage and the soma voltage on the same plot so we can see them side by side. That should be all we need. So we're going to go ahead and click Create Network in the upper right. And we're back to our cells here. Let's go ahead and make them colorful. All right, and now we can see, the 2D connection plot is still there, but the traces are blank because we haven't run our simulation yet. So let's go ahead and get out of here. And our little rocket there launches the simulation. Alternatively, you can always go to the menu bar, click Model, and click Simulate Network. But the rocket is a nice little shortcut to that. All right, so let's look at our traces. All right, so our traces showed up. This is cell 0 of population E. And I'm going to turn off the hover information. So these little guys here are the hovers. You can get more information by hovering over the plot, but it gets a little distracting. In the legend here, it's pretty cool. You can click and turn off any variable there. So you can look at them one at a time. We can see the dendrite doesn't spike up as high. The soma obviously gets a much higher spike. And if we look, let's go ahead and zoom in here. I'm going to click on wheel zoom, one of the tools over here on the plot. And I'm going to zoom in. I also want to be able to move it. So I'm going to move it to the middle, zoom in here. And we saw that at 20 seconds, we put a current pulse into the dendrite. And we can see the dendrite shoots up first. And then that drags the soma voltage along with it until you get that first action potential. Let's reset our view. There we go. Now let's open up our raster plot. And let's compare these side by side. There we go. So yeah, so here's the raster plot. This is how cells spike through time. And cell 0 on the bottom here is the cell we've recorded from. So you can see that every time there's a little raster on the plot here for cell 0, that's where cell 0 is spiked. The first spike that happens is in this cell 0 at time 24, gets a current at 20, and then takes 4 milliseconds for it to cause the cell to spike. And that's enough in this network to cause spiking to continue all throughout the population. Obviously, we had to tune the network to get this. You can't just get this randomly. And yeah, so there's lots of plots. This is the spike histogram. So if we, let's put the spike histogram down here, and we'll put the raster up here. And you can see, yeah, comparing to the raster, there's no spikes at first, and then it starts spiking, and then the spike histogram goes on. There's a variety of spike statistics you can plot with only one population. It's not very interesting. The power spectral density. So this is has the most power at the lower frequencies here. And so on. This is just a very simple model, but that shows you how you can explore this in a variety of ways. And yeah, so that's it for tutorial 1, a very simple single population network with one cell type. Yeah. Okay, so any questions or comments or anything? And someone's going to have to talk because I can't see the chat screen when I'm...
Maybe I just mentioned that for people who are having issues, they can just load the completed tutorial.
Yes.
So if you go to File, New Blank, you will clear whatever you did, and then you can just go to Tutorials. Yeah, Joe is showing here. And then you can just go to the Tutorials menu and select Tutorial 1. And so if you run that, that should work straight away. And then I guess you can try it again step by step using the slides or the video recording from this meeting.
Yep. Yeah, so yeah, again, all that tutorial we just did, all of it is available just by clicking here. It'll load it all and so on. Every time you want to start something new, though, you do have to remember to do File, New, Blank. That's going to clear the kernel and get rid of any problems. Start from a fresh slate.